Good afternoon, everyone. We now move on to the next session. So we have a presentation on future of powertrain, shift towards electrification and hydrogen economy. There's a slight change in our schedule for the day. In place of Ms. Veena, we have Mr. Rohit Nair from Bosch, who will be delivering the opening remarks. I would kindly request Mr. Rohit to take over, please.
Yeah, thanks a lot, Parvati. I hope I'm audible.
Yes, please.
Yeah. So, good afternoon, everybody, and welcome to this session. I think this is a very important session from where we are standing today, because this literally talks about the future of how our vehicles are going to look at. Historically, the automotive industry has been governed by emission regulations. Euro 5, Euro 6. In India, we've had BS4, BS6. In the last decade, CO2 emission regulations have come into picture very, very prominently. For example, CAFE regulations in Europe by 2015 and 2020 for the PC and LCV segments. So far, all these regulations have been a stepwise reduction to pollutants. And recently, the word zero emission has been the vision for all the developed countries. But what's actually driving them? One of the main drivers is air quality. Recently, climate crisis has been gaining a lot of traction, and there's a social pressure on world leaders to execute stricter policies and regulation toward net zero emissions by 2050. As you all know, Europe and North America have already pledged for a net zero emission by 2050. In line, Europe already envisions only zero emission PC and LCV vehicles by 2035. I mean, these are big statements if you look at the context of where we are evolving from an IC engine to something completely different, and that too in a short span of years. While the IC engine took 100 years, this is happening so quickly. We also see commercial vehicles will follow in the later years. To achieve this goal, battery electric and fuel cell vehicles are going to be instrumental. Coming to India, the air quality and climate crisis, oil import bill that we are paying every year will be the key drivers for e-mobility and hydrogen technologies. While the government has rolled CAFE and FAME policies, the hydrogen roadmap is currently being worked out. I won't take much time more. I would invite Dr. Akshay, who is a veteran in this field, to give a holistic view on how the future of powertrain looks like from his perspective. Over to you, Dr. Akshay.
Yeah, sure. Thanks, Rohit, and I should thank Dr. Taslim for suggesting CII to invite me for presenting today. And like I have already told Rohit that I'm not a management guy, I'm not an economist, so what we do is that we handle hydrogen on a in a chemistry lab. We work on fuel cells, we work on batteries, and so what I will be talking to you today is my perspective and what lies ahead for the people, for the mankind in terms of hydrogen economy. In the meantime, I would just share my screen. Is the screen visible?
Yes, it's visible now, Dr. Akshay.
Yeah, so I'm going to the full slide mode. Yeah, is it still visible?
Yes, please.
Yeah, so as I said, I would be giving my perspective on shift towards electrification and hydrogen economy. As I said, the term economy would have the sort of least important, in the sense, like from a chemist point of view, the economy is still there, but from a real economic point of view, it may not be there. So please don't consider it as cheating, because I would sort of in the least chemistry way, without having any any confusing equations, I would sort of explain you, or in the form of a story, on how we have seen hydrogen, the origin of hydrogen, as well as how we are sort of going on a way to generate it in a sufficient fashion. And in the meantime, I have given a slight nudge to electrification and sort of sidelined it. Kindly don't consider it as cheating, but then let us move forward. So what's the current scenario? The current scenario is that you see that the world's energy consumption is rapidly increasing. The fossil fuel sources are dwindling. In fact, I would just pull out my laser pointer here. In fact, if you look at the time frame that we are in here, we have already sort of peaked the conventional oil demand. But then, if you see the world energy consumption it's sort of ever increasing. So then, as I said, it is the diminishing fossil fuel resources, ever increasing energy demand, global energy demand. This has led to, as Rohit rightly pointed out, a surge in consumption of liquid petroleum, volatile fuel prices, and then to add to all that, there is an unacceptable amount of greenhouse gas emissions. So climate is something that even US has now started considering seriously, the climate changes. Is there a way that we can actually I would sort of show you what is the interrelation between not only hydrogen economy, even how to control carbon dioxide on a long run, and in addition to carbon dioxide, what are the other fine chemicals that would sort of play an important role in the years to come. And in brief, in the current scenario, what is at stake is the economic and industrial security worldwide, and this has led to the lookout for alternative fuels. Now, if you look at the simple pie chart of how the fuel distribution is there, you see that hydrothermal energy, solar contributes to about 15% of the energy that is, this is the alternate, barring the conventional oil. So wind is about 1/4. The contribution from wind is about 1/4, and biomass contributes to 43%. If you look into this, the geothermal, the hydrothermal, solar, wind, they all can be transformed into hydrogen. How is it? I will explain at a later stage. This is biomass is something that is indirectly transformed to hydrogen, but then solar, geothermal, wind can be directly translated to hydrogen energy. I would explain how is it. So what are the alternative sources? Solar energy harvesting is one alternate. Methane to methanol. Methanol is a fuel, and that is another alternate. Carbon dioxide to methanol is another alternate. Again, I said hydrogen would play a crucial role here in the future transformation of carbon dioxide to fuels and utility chemicals. So, can we have clean coal, petroleum technologies, biomass conversions, and how all of this could sort of interplay and lead to ultimate molecular hydrogen, which is clean burning? Because see, this is something that is very interesting, that like we have all studied this, how the universe has formed, like in class 12 in classical inorganic chemistry, that you all hated to study. There we saw in the Big Bang theory that everything started with the hydrogen, right? Like the small subatomic molecules forming the atoms, and then they all forming the most elemental or the fundamental molecule of hydrogen. And then we saw that all theories, quantum mechanics, they all were based on the simplest element, that is on hydrogen. And now even you see that in sun, it's the burning of hydrogen that is giving the energy. And still we right from the fundamentals of chemistry to this stage wherein we are looking ahead for the future for self-sufficiency in energy, we are dependent on molecular hydrogen. So this is sort of in the sense like this is sort of very interesting that hydrogen formed the initial basis of the elements, and all the elements that were derived was all the fundamental building block was hydrogen, and then we are still dependent on hydrogen as for attaining energy self-sufficiency, right? So then, if you look into this volumetric HHV of energy density of hydrogen, you would realize that the the volumetric HHV energy density of different carrier options. You would see that as you go from hydrogen to methane, as you go from hydrogen to methane to methanol. So I have given a comparison of both, that is gaseous state as well as the liquid state. You would see that at any pressure, hydrogen gas clearly carries less energy per volume than methane. Methane represents natural gas because that is something that is found in abundance in US, and methanol, propane, or octane, they represent gasoline. Now, at higher pressures also, the gaseous hydrogen reaches the volumetric energy density of liquid hydrogen. That's what you see here, that the energy density of gaseous hydrogen and liquid hydrogen are same when the gaseous hydrogen is at 800 bar. But then what is very important is that the common liquid energy carriers like methanol, propane, octane, gasoline, they surpass liquid hydrogen by factors of 1.8 to 3.4. But then you should understand that at such higher hydrogen pressures, this should be contained in highly pressurized containers, typically cryogenic containers, while the liquid fuels are kept in unsophisticated containers. So now the question is, if you see the gaseous hydrogen, liquid hydrogen, they need sophisticated containers, and the typical liquid fuels that we use on a day-to-day basis, and they do not require unsophisticated containers. So the question is, if we are making a switch from the conventional liquid to hydrogen, why do we make? In the sense, the operational procedures are very cumbersome, and is there a alternate? But then, if you look at the global hydrogen demand, you see that it is on a continuous raise. So the light blue, and this I have directly got it from IEA, the website, IEA website. You see that on a metric ton scale, it is on a linear rise all the way from 1975 to 2018, and it looks like it would go on a exponential rise. So where are they used? Hydrogen use today is dominated by industry, namely oil refining, ammonia production. See, that's what in the previous slide where I showed this in this portion, this represents that it is produced from refineries, and this represents that of the factors that is produced from refineries, the dark the blue color, it represents that this is used in ammonia. So ammonia production, which has brought about a renaissance in food industry, and which has increased the overall level of standards of living, global standards of living, requires a huge amount of hydrogen. So the classical Haber-Bosch process, wherein hydrogen is combined with nitrogen to give ammonia, requires a huge amount of hydrogen. So hydrogen is not only required for automobile industries, it is most of its demand lies in the ammonia synthesis. So yeah, as I said, that the industry is hydrogen utilization industry is dominated by oil refining, ammonia production, methanol production. Why methanol production? Carbon dioxide to methanol. I will come in detail at a later stage. Steel production. Virtually all of this hydrogen is supplied using fossil fuels. Fossil fuels, in the sense, I will come to the next slide, wherein we see that from natural gas, from coal, and a small fraction from water. So there is a significant potential for emission reduction from clean hydrogen. So in transport, the competitiveness of hydrogen fuel cell cars depends on fuel cell costs and refueling stations, while for trucks, the priority is to reduce the uh, delivered price of hydrogen. So shipping and aviation have limited low carbon fuel options available, and they represent an opportunity for hydrogen based fuels. In buildings, hydrogen could be blended into existing natural gas networks. So if you are having a gas pipeline, they could be blended with hydrogen, with the highest potential in multifamily and commercial buildings. Commercial buildings are some things that would benefit the most if you are considering of rationing hydrogen in buildings. So particularly in densities, while longer term prospects could include direct use of hydrogen in hydrogen boilers or fuel cells. So, power generation, hydrogen is one of the leading options for renewable energy, and hydrogen and ammonia can be used in gas turbines to increase the power system flexibility. Ammonia could also be used in coal fired power plants to reduce emission. So, see, on average, 70 million tons of natural gas is used to produce hydrogen. So, reforming process, and there are some technical aspects to it. In places where natural gas is in abundance, for example, Middle East, Russia, North America, the natural gas cost is less, hydrogen production cost is less. So hydrogen is available at a lower price. But then in China, India, and Southeast, so they are mostly importing natural gas. So then it would result in higher hydrogen costs. But then you should understand that there are a few bottlenecks. As I said, hydrogen could be obtained, a clean burning hydrogen could be obtained by splitting of water, which constitutes about 0.1% of the hydrogen that is globally produced. Most of them come from natural gas, and a slight amount from coal, and rest of them from oil. So a major component is natural gas, a slight component from coal, and the rest from oil, crude oil. Now we are looking, in the sense chemists are looking whether they can do the same thing. Can they accomplish hydrogen generation from biomass? That is something that is a emerging field of research. But then you should understand that hydrogen does not exist in nature in its pure state, but it has to be produced from sources like water and natural gas. The synthesis of hydrogen requires energy. Ideally, the energy input equals the energy content of the synthetic gas. Hydrogen production by any process, example electrolysis, reforming, or else, is a process of energy transformation. Electrical energy or chemical energy of hydrocarbons is transformed to chemical energy of hydrogen. Unfortunately, the process of hydrogen production is always accompanied by energy losses. Hydrogen can also be extracted from hydrocarbons by refining. This process is in principle an energy transfer process. The HHV energy that is contained in the original substance can be transformed to the energy of hydrogen. Theoretically, no external energy is needed to convert the hydrocarbon. Hydrocarbon in the sense, it is either methane here, or crude oil, or coal. But in reality, thermal losses cannot be avoided, and the energy content of the original hydrocarbon fuel always exceeds the generated hydrogen. So the efficiency of hydrogen production is about 90%. Consequently, carbon dioxide is released by this detour process than direct use of hydrocarbon precursors. But no obvious advantages can be derived with respect to well-to-wheel efficiency and overall carbon dioxide emission. For most practical application, natural gas can do what hydrogen also does. Therefore, there is no need of a conversion of natural gas to hydrogen. which is difficult to package and distribute. The source energy, electricity or hydrocarbon, can be used directly by the consumer at comparable or even higher source to service efficiency and lower overall carbon dioxide. So all these factors, see, that's what I said. Making hydrogen from electrolysis, making hydrogen from hydrocarbons, it is a energy intensive process. So what happens is, the question is, why would we transfer hydrocarbons to hydrogen, or why would we do electrolysis of water? And also, what the question to be answered by the chemist at the moment is, what do we do after we run out of hydrocarbons? What do we do after we run out of fossil fuels? And currently, why do we transform hydrocarbons to hydrogen if transporting hydrogen is difficult? If we have to use laborious techniques to pressurize hydrogen and then pass it through gas pipelines, why should we do that? Is there a safer alternative? Is there a less economical? Is there a more economical alternative? Is there a inexpensive route? These are some of the questions that we are as chemists we should answer. So now, but then still there is a lot of hope with this hydrogen economy. It's typically considered as a sunrise industry, but then there are a few bottlenecks. So these are the bottlenecks. When ultimately pure hydrogen comes out, it has to go through all this. So there are challenges in packaging. It has to be compressed, it has to be liquefied, and it has to be transported via surface vehicles or pipelines, and it has to be stored. Where do we store? In order to store it in cylinders, it has to be compressed or liquefied. In order to sort of transport it, if it is in the gaseous form, you have to use pipelines. Can we use solid materials? These are, see, the volume available for fuel tanks is limited. Also, the diameter of the pipelines cannot be increased at will. So to contain more hydrogen, you cannot increase the diameter of the pipeline, or you cannot operate at very high cylinders. So, and even more energy is needed to compact hydrogen by liquefaction. Theoretically, about 4 megajoules per kilogram energy is removed when you liquefy hydrogen gas, which is much less than its energy content. The energy content of hydrogen is about 142 megajoules per kilogram, but then it is not so simple calculations. For example, if you are having a liquefaction unit, if you are having a liquefaction unit that is producing hydrogen at 10 kilograms per hour, then it needs about 100 megajoules per kg of energy, whereas 1000 kilogram per hour hydrogen production unit requires only 40 megajoules. So it is not so straightforward calculation, but then the bottom line is liquefaction, compression and storage of hydrogen in cryogenic cylinders is very cumbersome, and more cumbersome is transporting them in pipelines. So is there a alternative? Can we use hydrogen storage, solid storage materials? Solid storage materials can also be physical absorption or chemical absorption, but then there are some downsides also. What is the downside? The metal hydrides, physical storage materials or chemical storage materials, can store only about 55 to 60 kilograms of hydrogen per meter cube, in comparison with 70 kilograms of hydrogen for liquid hydrogen. So, on the other hand, if you consider methanol, it can store about 100 kilograms of hydrogen per cubic meter. This is something very important. So, gaseous hydrogen is less economical. Much less economical is solid hydrides. but then liquid hydrocarbons such as methanol could be more economical. So we typically call it as liquid organic hydrogen carriers. So anyways, I would skip this slide on what are the targets, but then this is how. So uh, liquid organic hydrogen carriers can come to the rescue. How would you do that? I have showed you that the electricity that is generated from solar power plants, uh, I'm sorry, the electricity that is generated from solar power plants can actually um, be used to electrolyze the water. Hydrogen is generated, and that hydrogen, instead of transporting, what you do is you do a hydrogenation of this organic carriers and then transport the organic carriers. Once you transport the organic carriers, you do a dehydrogenation to once you transport the organic carriers to the destination, you do a dehydrogenation and use the hydrogen that is produced for mobility, fuel cells, and industrial processes. The cost of transportation of liquid organic hydrogen carriers is less, and it is easier to handle than bare hydrogen gas or the metal hydrides. So that's what I said. So when you remember the one of the first slides that I showed, where I said that wind energy, solar energy, geothermal energy, hydrothermal energy, all those can be electrified. The electricity that is generated can be used to do electrolysis, water splitting, to generate hydrogen, and this hydrogen can be stored in organic hydrogen carriers, which can be transported easily to the place of destination, and it can be dehydrogenated. And when you do the dehydrogenation, the hydrogen that is generated can be used for a variety of applications. On this note, I would, since I'm nearing the time scheduled for my talk, I would just give you a glimpse of some of the work that we do in our laboratory towards hydrogen generation. And as I said, these are all interrelated. Why is this interrelated? Is that biomass, coal, these all can be very nicely transformed, very conveniently transformed to specialty chemicals. In the process, hydrogen can be liberated, and this hydrogen can actually be used to mm, uh, do a lot of it has a lot of applications, industry and electric in industry, energy storage, and so on. In addition, this hydrogen in turn can be used to sequester carbon dioxide. Hydrogen can be used to transform carbon dioxide to methanol. Methanol in turn is a good source of hydrogen, so they can be used in a cyclic fashion. You react hydrogen with carbon dioxide, store it as methanol, you get the hydrogen back from methanol. So methanol is a hydrogen carrier. Dehydrogenate methanol to get hydrogen and carbon dioxide, and when you want to store it, rehydrogenate carbon dioxide with hydrogen to give methanol. So what we do is that we use for this purpose, we use typical catalysts that look like a crab. You can see the mouth of the crab has the metal, and the two side arms are typical organic fragments. And you see, in contrast to a bare metal which is typically naked, here it is surrounded, so it is holding, it is controlling what is happening at this site. And in this process, what we have shown that we could use very abundant glycerol to lactic acid and hydrogen. So why glycerol is important? You see, when this conventional oil sources have come down, biodiesel production has taken its place. One of the significant byproduct of biodiesel production is glycerol. And this glycerol is a liquid organic hydrogen carrier. So glycerol can be transformed to very useful lactic acid, which has several applications as biodegradable polymers and food additives. And when this transformation is done, the hydrogen that is generated is a bonus. Similarly, ethanol could be transformed, low energy density ethanol could be transformed to butanol using this catalyst, but not of importance in this talk, because this talk is mainly on hydrogen economy. Butanol is a future fuel additive because of its high energy density. But then, yeah, that's what I said, that these catalysts, I will go through it because these catalysts are very effective because of mainly because of the three portions. They are holding the metal and controlling the reactivity. So what we do with this catalyst is that we provide it an alternate way so that we can transform coal, we can transform biomass, we can transform methane, and go all the way to fine chemicals, including hydrogen. And you should understand that this hydrogen is very useful in transforming nitrogen to ammonia. Ammonia is one of the basic nitrogen supplier for the nitrogen fixation chain, right? So it is ammonia synthesis. The Haber-Bosch process has brought about a renaissance in healthcare products, in food industry, and in improving the overall health of the human population globally. And you should understand that in places where ammonia is required and where nitrogen is in excess, you can produce ammonia. And in places when from biomass where ammonia, there is crude ammonia that is exiting, you can use similar catalysts that I have discussed before to transform this ammonia in a reverse direction to hydrogen and nitrogen. So there are places where you do not need ammonia. It is crude ammonia, it is in excess, it is produced in excess during waste management, biomass transformations. There, those ammonia, again, ammonia is a carrier of hydrogen. Ammonia can be decomposed to nitrogen and hydrogen. Similar to methane, similar to methanol, similar to hydrocarbons, the ammonia that is, say, waste from biomass degradation can be transformed in the reverse reaction to hydrogen and nitrogen. So similarly, the biomass can be transformed to hydrocarbons and then transformed to hydrogen. And so I'm not going to give you more details why alkanes. This, see, in when from hydrocarbons, you can get high purity hydrogen. Why is that? Because, see, light alkanes are highly undesirable. In the hydrocarbon fraction, only a small fraction of hydrocarbons are used as fuels. Higher quantities are waxes, lower hydrocarbons are gases. In gases also, methane, ethane, propane, they are useful. But then pentane, hexane, they are highly volatile. When you keep it at room temperature, they will escape off. Is there a way you can convert those to light alkenes just by removing one hydrogen? And that hydrogen will be pure, contrary to water splitting reaction where oxygen is a byproduct, where you get oxyhydrogen, where you have to have a membrane to separate oxygen and hydrogen. Here, in these cases, the alkenes are liquids, hydrogen is a gas, separation is easy. And the from alkenes, by removing a hydrogen, whatever alkenes that you obtain, they are very useful in specialty chemicals as precursors to polymers, rubber, synthetic rubber, and highly valuable monomers in copolymers. So this is what I said that time, that hydrogen can be used reversibly with carbon dioxide. So methanol, you obtain hydrogen, and then whatever hydrogen is generated and whatever other hydrogens are generated from hydrocarbons or bio waste, you treat it with carbon dioxide to get formic acid and methanol, which again serve as hydrogen sources. See, in places wherein ammonia is in excess, or in places wherein hydrocarbons are in excess, in places where you are doing a water splitting and generating hydrogen. Once you generate hydrogen, how do you transport them? What you do is you combine this hydrogen with carbon dioxide, transform into methanol, which can be easily shipped. At the destination, you dehydrogenate methanol to get back the hydrogen and carbon dioxide. So in this regard, that's what I said, that in our lab we have very good technology in transforming glycerol to lactic acid and hydrogen. Why is this important? Because of the shift from conventional to non-conventional fuels, biodiesel production is in excess, glycerol is in excess, lactic acid has a lot of values. In addition, the importance of hydrogen. So what we have done is we have transformed glycerol to lactic acid. And these are, again, glycerol can be considered as a liquid organic hydrogen carrier like methanol and ammonia. The other importance is that hydrogen finds utility in fuel cells. Fuel cells can be used for a lot of small energy requirements in portable devices such as mobile phones, glucose meters, point of care devices, tablets, breath analyzer, toys, and so on. But then again, how do you, if hydrogen transportation storage is difficult, you cannot consider connecting this fuel cell to a hydrogen cylinder. What are the other alternatives? Methanol is readily available, ethanol is readily available. Those can be dehydrogenated. Imagine that you are having a fuel cell, you are having a cartridge. Ethanol is readily available, right? You have a cartridge of ethanol, you connect it to this fuel cell, and the catalysts that are generated in our lab can transform this ethanol to hydrogen in situ. In situ in the sense at that instant. So it is an instant generation of hydrogen from the ethanol cartridge, and that hydrogen will power the fuel cell, will run the fuel cell. So and it is like a printer cartridge. You can carry 1 ml, 2 ml cartridges that you can carry, and you could power the fuel cells. So I would sort of stop here because I have exceeded 5 minutes, I guess. So I would end by saying that hydrogen is today enjoying unprecedented momentum. And that's what Fatih Birol said. The world should not miss this unique chance of making hydrogen an important part of clean and secure energy future. And our Pincer Catalyst, we have a lot of priorities. We are in each of these transformations. I am sure that most of the audience may not understand this, but then this is just going from hydrocarbons to olefins, which are precursors for polymers, hydrocarbons to aromatics. As I speak to you, as you listen to me, if you are all drinking waters, the PET bottles, these all contains aromatics. And when you generate aromatics, see, at the moment conventional oil is decreasing. So what is the source? The source has to be from biomass. Alkanes has to be obtained from biomass. Alkanes can be transformed to all these aromatics with their bonus molecule of hydrogen. So they can contribute to hydrogen production. Biomass, dehydrogenation to hydrogen, and the transformation of the hydrocarbons to variety of molecules that find utility in synthetic rubber, drilling oils, and as fuels, in addition to clean burning hydrogen. Similarly, you can think of transforming carbon dioxide using methanol as a fuel cell source and all, to using methanol as a liquid hydrogen carrier. So these are some of the priorities I have just shown to you for the if anyone of you are interested in what chemistry is happening in our lab. And I take this opportunity to thank both my supervisor, Professor Samuelson from ISC Bangalore, Professor Alan Goldman from Rutgers, and I acknowledge various funding agencies, Reliance Petrochemicals, Gujarat, Reliance Industries, and ISRO, BRNS, and so on. And by the way, IIT Guwahati is a very nice place. So this is not a Photoshop photograph. This is a real photograph of how beautiful the campus is. You can just type on YouTube and you can get a drone video of how nice the campus is. Definitely, some of the industry persons, when you are coming, if you are wishing to collaborate, there are a lot of opportunities for collaborating with IIT Guwahati. We have a Center for Nanotechnology. We have the Department of Chemistry. We all do cutting edge research on hydrogen production. Not only hydrogen production, synthesis of specialty chemicals, and so on. So do visit us, and I again thank the organizers for allowing me to talk in this platform. Thank you.
Thank you so much, Dr. Akshay. I think very, very insightful session, especially for industry veterans who are mainly concentrating on how to shift from ICE to hydrogen, but sometimes fail to take into account the methodologies that are in place. Like you said, the hydrogen is everywhere, but it has to be produced. There are energy losses. What do we do when we run out of hydrocarbons and fossil fuels? I think burning questions that we need to answer. We need to also take into account what is the safe and economical way of hydrogen transportation. And as you said, liquefaction, compression, storage all becomes very, very difficult. So if we are talking of a hydrogen economy going further, we need to look at further elements. We need to look at natural gas, for example, how methanol will play a critical role. I liked your point on the liquid organic hydrogen carriers. This is also a very good solution for transportation problems. And biomass is available freely today in India. We are one of the largest countries having biomass. And if we can get ammonia out of it, and that can be then converted to hydrogen, that would be a really good way to go forward. So I mean, very insightful session, Dr. Akshay. I think the industry today is looking for veterans like you to partner with in this space. And I would personally like to thank you and IIT Guwahati for coming up with this research. I'm sure after this talk, there will be a lot of keen people who would like to talk to you further on how do they proceed in the whole hydrogen economy journey. So thank you very much again, Dr. Akshay.
Definitely. Thank you, Rohit. Thank you.
Thank you. Over to you, Parvati.
Thank you, Rohit. Thank you, Dr. Akshay. It was indeed an insightful presentation from your end. Thank you so much on behalf of India Innovation Summit. With that, we come to the end of our session for the future of powertrain. We would now close for a short break, and we will come back at 5. We have the rest of the sessions happening from 5 to 8. Requesting all the participants to join us at 5 o'clock for the session on future of automotive and mobility. Thank you so much. Good day.
Thank you.